I'm very happy to start today with the 5th webinar of the online edition of the Protelec Electrostatic Conference. I'm also happy to say that the success of this initiative keeps increasing. Now we have 51 subscribers to the YouTube channel. Many people watched the live event. And I hope this number will soon reach the 100 on YouTube. Also, we finally have a longer timeline on our program, so you can have an idea of the speaker until the beginning of April. And today, it's a pleasure to have Robert Krasny from University of Michigan. So Robert has a PhD in applied mathematics, got the UC Berkeley, and then he did a postdoc at the Courant Institute, and then he joined the Michigan Department of Mathematics. Today, he will be talking about GPU-Accelerated Fast Summation Method. So, Robert, welcome today. The podium is yours.
Thank you very much, Walter. And I appreciate very much the opportunity to participate in the webinar, not only as a speaker today, but hearing the other talks. Welcome, everyone. Thanks for joining. So I'm going to tell you about this GPU-Accelerated Fast Summation Method, but it's in the context of protein electrostatics. And so first, to give you an outline, I'll first remind everyone about the Poisson equation, and then we'll look at the Poisson-Boltzmann implicit solvent model for solvated protein. And we use an algorithm called barycentric Lagrange tree code, BLTC, and we do GPU acceleration. So this is the rough outline. And looking at the Poisson equation, we can remind ourselves that if we're given a static charge distribution in free space, then we have an electrostatic potential. And there are many numerical methods, analytic numerical methods to solve for the phi, but here I'm interested in integral methods, integral equation methods. And so we can evaluate the potential as a Coulomb integral over the charge density. And if we discretize the integral using a quadrature rule and evaluate at some point xi, and suppose that the yj are the quadrature points, and we combine the charge density with some volume elements and get discrete charges, then we have to evaluate sums of this type. And there's two loops. We have a loop over I and a loop over j. And this is the direct sum, and it's well suited for parallelization. The reason it's well suited for parallelization is because it's very simple. And each calculation here for a given I and j can be computed concurrently with different i's and j's. And the computations for different i's and j's are essentially the same. And so those features make this very well suited for parallelization. However many cores you use, the cost will still scale like order n squared. So we'd like to reduce the asymptotic scaling and still preserve the good parallelization. And so that's what the goal is here. And I'm going to encourage questions along the way, if I hope that's okay. If anyone wants to, I'm more than happy to answer questions along the way. So we're interested in the Poisson-Boltzmann implicit solvent model. And I became interested in this working with Wei-Hua Gang around 10 years ago. And so we have this representation of a protein with discrete charges located at yk. And omega-1 is the protein domain. It has a dielectric constant epsilon-1. The solvent domain, the exterior, call that omega-2 with another dielectric constant epsilon-2. And gamma, the molecular surface, we're going to choose the solvent excluded surface for the interface. And we have mobile ions in the solvent. So this is the physical picture. It's a model, and it is described mathematically by two coupled Poisson type equations. We have in the protein domain, we have a Poisson equation for the discrete charges. NC is the number of discrete charges. And in the solvent domain, we have a linearized Poisson-Boltzmann equation. So the ions that are dissolved in the solvent in one theory have a Boltzmann charge distribution. And when that's linearized, it shows up as this term over here. And so kappa is proportional to the ionic concentration, kappa bar, the way this is. Now, we have other conditions to satisfy. So on the molecular surface, we have continuity of the potential. So the limit of the potential approaching gamma on either side must be the same. And the electric displacement is the same as well. This is the normal derivative, okay? We have a far-field boundary condition that the potential vanishes. And once we've computed the potential, the surface potential in particular, we can calculate the salvation energy. So we have to evaluate this term. The reaction potential is the difference between the potential that we're computing and the Coulomb potential just of the discrete charges. And so this is the quantity, or one of the central quantities that that the biochemists in particular are interested in, of course. Now, there are lots of Poisson-Boltzmann solver codes, and the most popular ones are finite difference methods. And so here's a list of the codes that I'm aware of. And however, we're interested in the alternative of the boundary element method. And these are 3 boundary element codes that have been developed. And Wei and I developed this TABI. It stands for Tree Code Accelerated Boundary Integral. And so I want to tell you about this code. And so we need to convert those differential equations that we saw here. We're going to convert them into boundary integral equations on the molecular surface. And we're going to solve for the potential on the surface and the normal derivative of the potential on the surface. And so we use a formulation that goes back to there was Berenson's group. Jufer was the lead author on that paper. And they wrote down the following set of equations. So first, let's define G0 is just the Coulomb potential. And G kappa is a screened Coulomb potential. So the kappa here is related to the parameters this way. And we're also going to need epsilon, the ratio of the dielectric constants. So these two Green's functions, these are the Green's functions for the Poisson equation and the linearized Poisson-Boltzmann equation. It's so, let's say, so there is a natural boundary integral form that people had been using, which turns out to be ill-conditioned. But what this paper introduced was this set of equations, which turns out to be well-conditioned. So let me point out what we have here. What's highlighted in blue is the potential and the normal derivative. And this is the one-sided normal derivative on the interface. And we're solving for both variables, and they appear here under these integrals. These are now surface integrals. We have some source terms. I'll show you what those are. And we have kernels, K1, 2, 3, and 4. And in this formulation, these kernels are given in terms of the G0 and the G kappa. K1 is the difference. K2 and K3 are differences of first normal derivatives, and K4 is a difference of second normal derivatives. But the important property of this formulation was that you have G kappa minus G0 here. So even though it's the second normal derivative, the difference over here weakens the singularity that would be present without this difference. And it's that property together with the form of these equations. These are second kind equations. They have a very good form. They give well-conditioned numerical methods. So I'll tell you that the source terms that appear over here come from the discrete charges, and this is a normal derivative on the interface, at a point on the interface. So it's a coupled set of integral equations to solve for the phi and the normal derivative. And then once you've got those quantities, then you evaluate this integral and you get the salvation energy this way. So we're going to use this formulation. And the way it works is you pick points on the interface, you replace the integral by a sum. Okay, so we need to triangulate the interface. And here's an outline of what the boundary element does. So we triangulate the interface, and then we discretize the integrals using the triangles that we have. That gives a linear system for the potential and its normal derivative, say at the centroids of the triangles. We solve that by geom-res, which requires a matrix vector product. We compute that using the tree code. And finally, we can evaluate the salvation energy. We call this method TABI. I'll pause for any questions. Okay, so that's it in a nutshell. And here's an example. So this is from the work that Wewa and I did. We picked a protein, the RNA binding domain of E. coli rho factor. It's got 2,069 atoms. Here's the schematic picture of it. Here is here's the triangulation. And I'll say more about the triangulation, that's coming, okay? But, and after running our code, we can plot the surface potential over here. So this is what people are interested in. And what we did a comparison with APBS. And so with TABI, if we, so this is a subset of results that we obtained. So using 30,000 triangles, we determined that the error in the salvation energy was about 6%. And that calculation back then took 130 seconds. If we refine the triangulation to 130,000, we can reduce the error. Of course, it's more expensive. Running APBS at that time, I would say this is from a paper in 2013. Running the APBS we had at that time, H was the grid spacing for the finite difference method. About 0.5 angstroms gave 5% error, and it took only 72 seconds, which was faster than the boundary element method. To achieve comparable error over here, the H had to be reduced to about 0.1, a little more angstroms, but that took much more time than the boundary element method. So the upshot here was that the finite difference method is fast on a coarse mesh, but to reduce the error to this level, the boundary element method was superior. It's a question of what error is acceptable to the user at the end. They had this choice. So continuing the story.
Sorry, Robert, may I ask you a question?
Please.
How do you evaluate the error? So,
good question. So we, because the answer is not known analytically. And so we extrapolate. And I'm going to show you a picture in a couple of minutes that will explain how the extrapolation works. So if you extrapolate to larger and larger values of n, you can estimate So for each value of n, each triangulation, you compute a salvation energy. And then you can extrapolate those values. And I'll show you a picture in maybe 5 or 10 minutes of how that extrapolation works. And the extrapolation is our estimate of the exact solution. And we do that for the boundary element method. We also extrapolate the values for the finite difference method. So we extrapolate to the limit of, let's say, infinite resolution in both cases, and we get an estimate for the exact salvation energy. That's the best we can do, and that's how the error was evaluated here. To help, let's say, fill out that picture, I'll show you, I have it in a few slides down about what that extrapolation would look like. So I'll proceed unless there's another question or comment. So a few years later, in the summer of 2016, TABI was installed as an external contribution in APBS. So Nathan Baker began accepting external contributions, and we were one of several groups that had their codes installed there as options in APBS. And this was done by 2 grad students, Jiawei Chen from Southern Methodist University with Weiwa Gang, and Leighton Wilson is here with me in Michigan. So they went to the Pacific Northwest National Lab for the summer. They converted Weiwa's Fortran code to C, so it would fit in APBS, and it's there now as an option. Now, continuing along here, so we've been developing a new version of TABI, and it has these features. So we previously used a Taylor tree code. We switched now to barycentric Lagrange tree code. I'm going to tell you more about that. We switched from centroid collocation to a node patch discretization. So Benzu Liu and Andrew McCammon had a paper in 2007, and they showed the benefit of using this node patch discretization. Jiawei and Weiwa developed a block preconditioner to accelerate the GMRes solving. And we had been using MSMS. We switched now to NanoShaper. And so I'm going to tell you now a little bit about, we did a comparison between MSMS and NanoShaper. So the quality of the triangulation is of course, very important in a boundary element. In fact, I think any of these codes. Here's an example. We pick another protein from a test set. And so the MS triangulation together with the surface potential plotted and the NanoShaper triangulation, at first glance, they look very similar. The colors are in the same places, but you begin to look more closely, you see that there are some places where the MSMS triangulation has very thin triangles, whereas we don't see those features in the NanoShaper triangulation. We did further comparisons of this nature. Here now for the same protein, and so here's the extrapolation idea, Walter. So if we look at the surface area and we compute triangulations using MSMS, using NanoShaper, and we increase the number of triangles. So going down in this direction is refining the triangulation. The surface area computed using NanoShaper, the surface area computing MSMS. They turn out to be very close, okay? Both curves can be extrapolated. In other words, just try to evaluate when n inverse equals 0. And that's how we would estimate the exact value of the surface area. It's just an estimate. So, but you see there's some differences. In particular, well, I'm gonna come back to the differences. Do the same thing for the salvation energy. Compute with, so the MSMS has a density parameter, NanoShaper has a scaling parameter. You choose those parameters so that you get finer and finer triangulations, and you see these results. So this is how we extrapolate. We just extend this curve so it hits this axis. That's our estimate of the exact salvation energy. And for any n, the error would be the difference between that value and the extrapolated value.
May I ask, I'm Guido Raus, do you have a way of estimating the convergence with respect to convergence of the electrostatic potential, say, at a specific point?
We did that too. We did that too. Yes, we have an estimate of the error for the potential at each point, and we took the norm of the we measured. If you look at the paper with WE from 2013, we also estimated the error in the surface potential and the normal derivative using this this same approach.
Thank you.
You're welcome. Now I have to correct what I just said. No, what the errors that I'm thinking about were the errors introduced by the tree code. And the errors in the surface potential and its normal derivative were compared with the errors, compared with the direct sum, not with the exact values, because it's the, yeah, I have to say, I just misinformed you with my answer. We don't have a good way, we didn't estimate the errors in the surface potential itself. The errors I was referring to were the errors in the tree code approximation to the direct sum. The difference, another important difference between the two codes is that at some point MSMS, so there's a limit to how large the number of triangles can be with MSMS. It simply doesn't produce results beyond a certain number of triangles. We didn't, the limit is much higher. I'm not sure we even reached that limit with NanoShaper. So the red curve extends to more dense triangulations than the MSMS. The other feature you see is that in general, the NanoShaper results are smoother. And so it means that the extrapolation is going to be, let's say, better. The wiggles that you see here make it a little more difficult to get a valid extrapolation. So, but that's only part of the story. The other part of the story, on a test set of 38 biomolecules, and I need to keep time, oh, time is flying, okay. On a test set of 38 biomolecules, so we use 5 different values of the density, 5 different values of the scaling parameter. We get lots and lots of triangulations. We look at the average aspect ratio of the triangles. So for MSMS, there can be triangles with very large aspect ratio. The aspect ratio, the ideal aspect ratio is 1 for an equilateral triangle. The NanoShaper aspect ratios are smaller. If we look for any particular triangulation, we look at the largest aspect ratio. MSMS produces some triangles with very large aspect ratio. NanoShaper doesn't. And this affects the convergence. So the number of iterations required to reach a tolerance in the GMRes, the MSMS requires more iterations, and that converts into runtime. So the NanoShaper is able to reach a certain tolerance in less runtime. And so Leighton Wilson and I have a preprint now in which we're doing this comparison of the two codes. But the version of Tabi that's it's actually already installed in APBS is using NanoShaper as the default. And so to talk about now, go back to the question of how to compute particle-particle interactions. So think of the xi here as a set of target particles, the yj as a set of source particles. And I commented already that this is well suited for parallelization, but the cost is ordered n squared. There are a number of fast summation methods. There are mesh-based methods, and there are tree-based methods. And I'm going to focus on the tree-based methods. In particular, I'm going to focus on a tree code, although we use elements of all three of these right now. So what is a tree code? Here's the idea. To evaluate this sum, we break it down into a sum over clusters. So this is a sum over all source particles. C here represents a set of clusters of source particles. Okay, and then the xi interacts with the yj's that are contained in a particular cluster of source particles. Now, there are two ways to evaluate this. We call this a particle cluster interaction. There are two ways to evaluate this, and it depends on whether the cluster is near or far from the target. If the cluster is, if the yj's are near to the xi, we do a particle-particle direct sum. That means we evaluate this by looping over j explicitly, as you see. But if the yj's in this cluster are far from the target, we can do a particle cluster approximation. And that works as follows. Okay, so we build a tree of particle clusters. And so let's say in this case, the targets and sources are the same. And the tree has one cluster at level 0. It has 4 clusters. Of course, we do this in 3D. Here, there are 4 clusters at this level, 16. Now, at some point, we stop dividing clusters. Okay. A particular target particle can interact. For example, let's take this target particle over here. This target particle can interact maybe with these 3 using an approximation, because these 3 clusters are far from this target. Okay, but it can't interact with these because they're not far. Okay, but if we go to this level, that particle can interact with these, again, perhaps using the approximation. Okay, I should say at this point, when these particles are as close as they are to this, we would switch to the direct sum. Now, what is this particle cluster approximation? Oh, first, what's the criterion for determining whether a particle and a cluster are well separated? So again, focus on a single target particle and examine all the clusters. We look at the radius of the cluster and divide by the distance from the target particle to the center of the cluster. And this is a user-specified parameter. And if this ratio is smaller than the epsilon we chose, then we can do this approximation. I haven't told you yet what that approximation is. That's going to come. The approximation is going to use this, a separated kernel approximation. So the x and y variables here are tightly coupled, but kernels can be expanded into this kind of approximation. Functions of x times functions of y. And once you've got this approximation, okay, then this particle cluster approximation that we see here can be approximated simply by taking this expression for G and plugging in it here, and then interchanging the two sums. Okay, you get this expression. This is the particle cluster approximation. And what is the benefit of this? These quantities here are independent of the xi's. They can be computed once and for all and used for different xi's. So the end result is an algorithm that has scaling like n log n. There's an error, but we can control the error by the number of terms we keep in these approximations. And what I'll say is that the n over here, that factor is related, that's just the number of target particles. We need to do this for every target particles. And every target particle interacts with clusters at different levels of the tree. And in general, there are log n levels of the tree. And so that's heuristically where this comes from. Now, I want to give some examples of separated kernel approximations. So there are such approximations that are kernel dependent. In other words, this specific kernel, the Coulomb potential, has this expansion in terms of spherical harmonics. And it's a classical approximation. It was used in the fast multipole method. The x variable over here, the rx, theta x, phi x, those are the spherical coordinates of x, and similarly ry, theta y, phi y, spherical coordinates of y. And the x variables are here, the y variables are here. Another example, you can take a kernel, you can do a Taylor approximation, where you expand with respect to the y about yc, the center of a cluster. And you have the Taylor coefficients, and you have these increments over here. And again, these quantities here only depend on x. These quantities only depend on y. So it's a separated kernel approximation. Wewa and I used this in our original tree code for Tabi. But later on, people began to look at kernel independent approximations. So there was the kernel independent FMM, the black box FMM, and we've been developing barycentric Lagrange tree code. It's based on barycentric Lagrange interpolation. Now I'm running out of time, and there are two possibilities. I could start speaking faster, but that is probably not a good idea. So I think I'm going to have to skip some slides. Let me simply say that the barycentric Lagrange interpolation over here we found is able to achieve the two goals that we wanted. Remember, we wanted to have scaling better than order n squared, but still be well suited for parallelization. And that's what this enables us to have. So that's the punchline. If I don't get to cover all the details, we can discuss it. This slide is meant to introduce barycentric Lagrange interpolation. I'm really just going to give you now, just touch the high points here. There was a paper by Jean-Paul Barut and Nick Trefethen. It was in 2004 in SciEM Review. And I looked at it at the time and I said, that's interesting, and didn't think about it again until about 3 years ago. And then we started using it in our tree code. It turns out to be very good in that context. It's very good in other contexts as well. I'm just going to have to go on. Tensor product extended to 3D. The same idea. So in this context, the separated kernel approximation looks like this. So these are Lagrange polynomials evaluated at source points. And this is a target particle. This is now evaluated at new source points. These are Chebyshev points. I have a picture that's going to help. Pictures are so good. So if we originally have a interaction between a target particle and a set of source particles, Yj, we can replace those source particles by these SKs. These SKs are Chebyshev, tensor grid of Chebyshev particles. And we get an expression, we get an expression where the particle-particle interaction, you get another particle-particle interaction, but it's a different set of particles. These are proxy particles and proxy charges located at the Chebyshev points. And the point is that the original direct sum here and the approximation have very similar properties. The G's over here are the same kernel that we have over here. They're just evaluated at different points. And so this barycentric Lagrange tree code is well suited for GPU acceleration. whether we do a direct sum or whether we do an approximation, these over here are very well suited, again, to be mapped to GPUs, because the terms over here in our approximation, again, for a given I and a given K, these terms over here have the same arithmetic cost. And so all of these terms can be computed concurrently. And GPUs are perfect for that. So just saying that in a nutshell. Here's an example with a million particles interacting by the Coulomb potential. Our theta parameter, this is the degree of the barycentric Lagrange interpolation. So comparing the runtime as a function of the error, this is now the error in computing the Coulomb potential that we see here, the phi i's. The top results were obtained on 6 CPU cores. The bottom results were obtained on 1 GPU. We can get errors down to almost machine precision. The red lines going across are direct summation. And these lines are tree code results for the 3 different values of theta. And so tree code, this is running on CPUs. The tree code is faster than the direct sum using 1 million particles. And depending on what error you need, you would pick the right value. But on a GPU, the direct sum speeds up a lot. The tree code still maintains its advantage over the direct sum for this number of particles. So Nathan Vaughn and Leighton Wilson did the GPU implementation of this. And now we put this into Tabi, and it's time for me to make my summary. So I wanted to tell you about the Poisson-Boltzmann implicit solvent model using our boundary element method. I had to rush through the description of the barycentric Lagrange tree code, but in fact, recently, the last year, Nathan and Leighton have developed this barycentric Lagrange. It's a dual tree traversal. It's a more sophisticated, it's like a fast multipole method. It has linear scaling. So actually, the Tabi that's available now is using this. I didn't have time to tell you how to go from here to here. It's GPU-Accelerated is our emphasis. So the collaborators on this work, Wei-Wa, a longtime collaborator, and his student, who's now at Michigan State as a postdoc, and Lei Wang and Svetlana Chlupova, former student, former postdoc, they did the original development of the barycentric Lagrange tree code. And Leighton Wilson and Nathan Vaughn, 2 current students, actually Nathan just graduated and is at Los Alamos, but they did the GPU implementation and the extension to the linear scaling method, which I didn't have time to tell you about. And just want to tell you that we have various projects going on now using these methods. And we hope in the future, we believe we can have maybe try to make a faster method for doing generalized Born. But on the other hand, I become aware of the importance of having better models for polarizability in the protein interior. And we're thinking about ways of doing that. So my last slide is just to say thank you. And these are pictures of Michigan in a different time of the year. So are there any questions at this point?
Okay. Thank you very much, Robert. That was a very interesting presentation. So I have actually a couple of questions before other people may raise their hands. So you, if we consider for a moment just the problem of a set of interacting charges, so no plus one, so no dielectric for the time being, how would you compare pros and cons of your approach to particle mesh Ewald approaches?
Yeah, I mean, most particle mesh Ewald is with periodic boundary conditions.
Yes.
So now we can accommodate periodic boundary conditions. I'm going to refer you to a paper by Henry Boateng, which appeared in JCTC last year. He's a former student of mine, and he worked on tree codes. And he did a comparison of his tree code method for the problem that you expressed with a PME. Let's see, I forget. Yeah, he was using DL Poly. So he used the PME in DL Poly, and he ran MD simulations. Now, he did his implementation of periodic boundary conditions was very simple. It's the following thing. He took the fundamental cell and he replicated it with a 3x3 grid. And then he did interactions between the fundamental cell and that single shell of replicas. And he did comparisons to show that he got essentially equivalent results with PME.
But my question, so I'm not very much worried about, so actually removing the constraint, so in many cases, let's put me in this way, in many cases the periodicity, the 3D periodicity is more a constraint than a desire. So if we could have, so there are people, for example, which are working on fast multiple methods in order to replace the particle measurable and having less constraint in terms of, so my point was more on the computational cost. So are they, and robustness, of course, accuracy with respect to particle measurable. So you said n log n, so they scale equally, basically.
Yeah, they're both, well, n log n for particle mesh Ewald, n log n for the tree code, but we have this new linear scaling method, BLDTT. So we're using some fast multipole ideas here, but it's based on barycentric Lagrange interpolation.
Okay.
And so, and the special niche I think we fit into is that this is especially well suited for GPUs, whereas those other methods are less well suited. So I could maybe explain a little bit about why. So for example, if you're doing this, okay, so these spherical harmonics expansions are typically computed using recurrence relations. And so evaluating these for different values of L and M can take different amounts of time. And if you assign this computation to a thread, you can have thread divergence for different values of L and M. And that's just not well suited for GPUs. On the other hand, in the approximation that we use, which is over here, so like over here, so you can assign this for each I and K, that can be done on a single thread of the GPU. And different threads can deal with different I's and K's. It's going to take the same amount of time. We don't have the thread divergence. Now, that I think is at the bottom of I think our method is going to be competitive with other methods that are
also in a possible molecular dynamics implementation.
Well, at every time step, we need to do the forces. I should say, we didn't extend our code. At the moment, we're not computing gradients, but we can, of course, by taking derivatives. So we definitely have MD simulations on our agenda to use these methods for. But it's going to be the users who tried the different methods and compare them, and in the end find one is better than the other. We try to do comparisons ourselves, but users also have to try. And,
thank you.
Yeah.
Are there any more questions?
Yes, I have a question. Thank you very much for the talk. So generally speaking, for electrostatic problems, can you comment on pros and cons of tree code versus fast multipoles?
So it turns out that tree codes are in general n log n. Fast multipole method is order n. Now that's from a high level point of view. There's always a prefactor that you need to be aware of. There's complexity. Tree codes are simpler than the fast multiple method. And the key issue though is parallelizability, if you have several choices, we need to have methods that work well on parallel computers. And it could be that a simple method has better parallel efficiency than a more complicated method. So you have to not only pay attention to the operation count, these are operation counts. We need to pay attention to the memory aspects and the communication aspects. And so, for example, PME is based on FFT in many cases. Doesn't have to be, but most PME codes, I believe, are using fast Fourier transforms. And in 3D, you have to work hard to get those to have good parallel efficiency. So tree codes don't use FFTs. They use different technology. And there is no simple answer except if you try you try the two things and find which one gives you the answer faster and more accurately. I will say that there were, for the Poisson-Boltzmann model that I told you about there are fast multiple codes, but I don't think they don't have equivalent results to what we presented. And I think the reason is because the fast multiple method is more complicated. It uses more memory than a tree code. Now, you might ask over here, I said that we're using tree code, we're using fast multiple method ideas over here, we are. So in the end, it's sort of like picking the best parts of different algorithms and packaging them up in the best way. And for us, we realized that the barycentric Lagrange was going to be good on GPUs, so we focused on that. And we evolved from using tree code ideas. This DTT, it means dual tree traversal, but it's essentially like a fast multiple type idea. And so we picked up some parts from the fast multiple method and put them together over here. So in a way, we're trying to insinuate ourselves into the FMM community. And we'll see if we're accepted or not. But we certainly have. In fact, I have the pictures here if you want to see. Let's see, I did make some extra slides here. This is this BLDTT algorithm. But let me not get to the details of it. Yeah, this is a good comparison. So this picture here, this is time and this is number of particles. And it's just a direct sum of Coulomb potentials. But we set the parameters to get about 7 or 8 digit accuracy. And the direct sum shoots up like this. This is log scales. So our BLTC, the tree code, those are the red markers. And this I should say, it's like a barycentric Lagrange using some fast multiple ideas. It's the blue over there. Now, the dotted line here, that's n log n, okay? And so the tree code is asymptotic to n log n. The dashed line here, the dashed line is n squared. And this one over here, it's asymptotic to n, sorry, this dot dashed line, that's the order n squared. This dashed line over here, that's order n. And this guy over here is asymptotic to that. So it's faster. So we find an advantage now for this BLDTT. This is now the scaling. And so what these students did is they've got this running now on multiple GPUs with domain decomposition, open ACC, I should say. It's a strong scale. This is 64 million particles. So the tree code is up here, and this dual tree traversal thing is down here. And so there is an advantage to the O of n scaling algorithm. But we couldn't put this, I mean, if we were using the Taylor tree code, or you know, other kernel approximations, we couldn't get it on the GPU in this amount of time. We would just lose the efficiency.
Thank you, Robert.
You're welcome.
I would like to add that later in spring or beginning of summer, we will be organizing a smaller CCAM workshop, more on the numerical methods. I think, Robert, you're already aware of this. I don't know when exactly this will be due to the situation, but so I think part of the fast multiple community will be there, and probably it would be nice for you to present your approach in that with that people. So I hope I will manage to bring them to join the community. So we have a question from Antonio.
Okay, well, first, thank you for the nice presentation. My question is the following. The example you show at the beginning, which is a typical one, that people want to compute the electrostatic potential on the surface of the protein. But I mean, some of us want to do something a bit more complex than that. And actually, you mentioned at the end of your talk that you were also interested in pKa calculations. So my question is, if I want to do do calculations in a molecule where I only change the values of the charges, keeping the geometry, would that be particularly fast to do with this method? I mean, would you, in a sense, be able to save the green functions and just replace the charge? How does it work? Whether is this, for instance, compared with a finite difference where you would have to repeat the whole calculation for the new charge?
So you want to keep the geometry of the surface, but change the charges?
Right.
Well, we could save a little bit of time because we wouldn't have to recompute the triangulation. Right. And maybe some parts, you know, like tree code algorithms have 2 phases where you like compute some things, and we could probably reuse that. So there could be some savings, but I would have to think about it a little bit more. But that now I'm thinking though, but in a pKa calculation, one of the issues is the geometry changes only a little bit, maybe because a proton is going on and off. So the geometry changes in a little bit. We have to think about how to update the triangulation without redoing the whole thing, maybe. So
yeah, sure, right. I was thinking more in terms of, because in some models, for instance, in the way I do it, the protons are always there, actually, even when they are not. So it's an approximation, sure.
Okay, I see. You can just turn the charge off. And
yeah.
All right, okay. I have to think, it's a good question, of course, and I have to think if we only change the charges, what kind of, how can we take advantage of that?
Okay.
I won't give a definite answer right now.
Right.
There is a question from the chat from Mehdi Irani, who thanks for the presentation, asked whether this method is implemented in the Ember program.
Well, it's implemented in the 3D RISM module in Amber. Mm-hmm. So Leighton Wilson has been working with Tyler Luchko to do that, and not the full blown this is in the works. So what's implemented in there now is a Taylor tree code. Although I have to check with Leighton, he may have already implemented the barycentric Lagrange tree code ideas. But anyway, but it's not implemented in the rest of Amber. And, you know, it's just a question of finding someone to do that. I would love to do that and make it available as an option there. But that's the extent of of where we are right now.
Okay. Then there is a comment more than a question from Jim Warwicker. So he's recalling the electrostatic boundary calculation. The first one was from Randy Zauhar and R.S. Morgan in 1985. And so he was just wanted to remember the pioneer of this work.
Absolutely, the papers of Zauhar were very important for us to read, and you know, I had to make a decision on when going back to this page over here. Am I going to list all the authors or their codes? And I chose to list the codes, but certainly Zauhar's papers were and are important for sure. Now I see another comment down there. Yes, Jufer was in the Berenson group for sure. Yes, and our work is based on that. There's no doubt about that.
So is there any other question? Let me see on the YouTube chat. No, there isn't. So in case there is no other question, then let me thank again the presenter of today, Robert. Thank you very much for your presentation. And so I'll see you back next week with the Dr. Mulder presentation. Okay. Thank you.
Thank you.
Thanks, everybody.
You're welcome. Thank you, Walter.